What's going on, guys? Welcome back to the channel. In this video, we'll be talking about inverse functions and the horizontal line test. This is a direct follow-up to the one-to-one functions video that I made previously in the playlist, and it also shows a lot of applications. So let's hop right into it. So before we talk about a one-to-one function or a horizontal line test and an inverse function, all right, so we said a one-to-one function has like any other function has an input. It has a unique input and also has a unique output. So, meaning there's no two same values on the graph, like in this line here, and there's no repeated output. So, the easiest way to show it is on this on this straight line on this graph here, and pretty much there is. So, if we say at A, we have f of A. At B, we have f of B. So pretty much. These values are different, is what the function is saying, and f of A cannot equal f of B for it to be one-to-one. And the easiest way, and so pretty much, take a look here. The easiest way to see it is with the line y is equal to x, making a t-chart xy, starting from the negative direction and in the positive direction. So I just did a couple examples. So if we plug in 0. We get 0, 1, 1, 2, 2, pretty much. And no matter in the negative direction, no matter in the positive direction, the values do not repeat at all in this line. And so we say the function is one-to-one. Okay? So an example of a function that's not one-to-one, let me just draw this graph out, guys. Sorry for the shakiness. Jesus. Sorry, guys. Alright, so drawing a similar graph out. Alright, a parabola is the easiest way to go. Okay, is the easiest way to show. Alright, the y is equal to x squared. Alright, so at negative a, think about this. At negative a, if we plug in a value a, well, it's going to be f of a on this side, and because x squared, by the properties of the functions of polynomials, which we'll cover later in the playlists, it mirror images on the with respect to the y-axis. So pretty much there's another value at a. So both these values are the same value, f of a. So because there's two direct outputs for two. So there's two unique inputs for every, or there's two unique outputs for every inputs. Pretty much, there's no output. But because they're repeated, it's not one-to-one. All right, and so that also tells us that also brings in the horizontal line test. So pretty much, the horizontal line test says, okay, if we take a line. All right, so. Sorry for the shakiness, guys. Going back up to this line, if we take our pencil or pen, in this case it'll be a pen, and we're going to make horizontal lines going all through every point possible on the graph. If it only touches one point horizontally, the function's one-to-one. So in this case, so this line y is equal to x is one-to-one, because if we take our pen. Oops, sorry about that. It would only touch one point, and you can see that graphically inside your guys' head. In some cases, all right, it's like x squared. Easiest way to show it touches 2 points on the graph. All right, and I drew a line to show. All right, so in this case, if we draw a line on the binder paper, drawing a line, it touches 1 point on the line. So that makes sense. That's one-to-one. So, but why is this important? Well, so it's important when we talk about inverse functions. All right, so an inverse function so an inverse function is pretty much so it's a function reflected across y is equal to x. The line y is equal to x. All right. And so graphically, that's the way I say it, and it only works with one-to-one functions. All right, and we'll show you guys how to do that algebraically in a second. But pretty much, if you do, say we have a curve right here. Okay, we're going to take that curve and reflect it across, make a mirror image across this line, y is equal to x. Sorry about that, guys. And we get something like this. Okay. It should be the same. Horrible, actually, something like that in this quadrant here. So pretty much, I'm sorry guys, I'm horrible with that. Be something like this. And funny to find out that this is what we call a rational function, or hyperbola in this case. But an inverse function in this, all inverse functions are one-to-one. So any one-to-one function could be inverted, and it reflects across the y is equal to x. Okay, so pretty much, also what this does is it also switches the domain and range. So switches x and y. So if you guys think about it, okay, so case y is equal to x, okay? Okay, so, alright, if we were to invert this, it wouldn't, so it gets reflected across the same line, y is equal to x. And so, it would be the same line. So we switch x and y, and the values stay the same. So, the easiest way to show is x, y, negative 1, 0, 1. It'd be negative 1, 0, 1. And if we were to switch y and x, y with x, we get negative 1, 0, 0, 1, 1. That's the easiest way to show inverse. So an inverse function switches x and y. All right, so let's do an example algebraically. All right, so let's make up a function. Y is equal to 3x plus 2. Okay. So we want to find the inverse of y is equal to 3x plus 2. Well, we could graph points or switch. So we could plug in points and switch them, but that takes too long. So algebraically, what we could do, as long as the function's one-to-one, and I'll show another example of why that's important. So if we switch. Alright, so now we need to invert, we switch x and y. So, alright, so meaning we have x is equal to 3y plus 2. So for any value of x gets switched with y, and we solve for y. So we're going to subtract 2 on both sides and divide. Okay, and this is so making this a line. So this is this is y is equal to 1/3 x minus 2/3. All right, so that's an inverse function. All right, but now I said as long as one-to-one. What happens algebraically if a function's not one-to-one? If we get multiple values that touch the function, or if we get multiple output values for the same function. So the easiest way to show would be with this example. Y is equal to x squared minus 4. A difference of squares, and we know all parabolas are not one-to-one. All right, and we'll say it has no inverse. But why? Okay, so algebraically you could switch x with y. Alright, x is equal to x is equal to y squared minus 4. Okay, solving algebraically, we have x minus 4 is equal to y squared. And if we take the square roots, y is equal to plus or minus the square roots of y is equal to x, y is equal to plus or minus the square root of x minus 4. Right? So pretty much, there's two points. Sorry about that, guys. I'm going to zoom in real quick for a second so I can draw a function. Sorry, guys. Still don't have my camera stand. I do need to get one of those eventually. But pretty much, all right. So it looks something like that. It'll be shifted to 2. So let's just say that's 2. Okay, we start at 2. Okay, so the general shape of the graph looks like this, and it fails the vertical line test. You guys look, it fails the vertical line test. All right, it should be at 4. My bad, guys. All right, it's not a function because it fails the vertical line test because of the plus and minus part of the function. All right, because we graph plus x minus 4, and we graph x minus the minus portion of the function. Well, it's not a function because it fails the vertical line test. It's not invertible. There's no inverse for it. Sorry about that, guys. There's no inverse at all. And so essentially, all right, whenever so it's not invertible, no inverse, because the possible inverse the possible inverse fails. All right, I hope this. So pretty much, there isn't an inverse because it fails the vertical the vertical line test. So this is technically not a function. We can't have a plus and minus portion of the function because then, well, there's two different input values for the domain and output, and so the function has two different output values for the same value. And with that being said, guys, we're going to call it quits for the day. I'll see you guys next video.